Good morning. My name is Rana Fatima and I am from MCA. Today I am going to present a seminar on the topic closure properties of regular languages, which is a very important topic in theory of computation. This topic tells us what happens when we apply different operations on regular languages. Now let's go to introduction of regular languages. A regular language is a language that can be recognized by a finite automaton, either a DFA or an NFA. It can also be described using a regular expression. In Chomsky's hierarchy, regular languages are at the lowest level. They are also called type 3 grammars. They are the simplest class of formal languages. For example, the set of all binary strings that end with 0 or all strings over A and B that contain an even number of A's. These are regular languages. Now, what's closed under mean? It simply means if you take two regular languages and apply an operation on them, the result should also be a regular language. If that is always true, we say regular languages are closed under that operation. Think of it like addition of integers. If you add two integers, you always get an integer. So integers are closed under addition. Similarly, regular languages are closed under many operations. The ones we will study today are union, intersection, concatenation, clean star, complement, difference, reversal, and homomorphism. Let's start with union. The union of two regular languages L1 and L2, written as L1 union L2, contains all strings that are in either L1 or L2 or both. To prove this is regular, suppose M1 is a DFA that accepts L1 and M2 is a DFA that accepts L2. We can build a product construction DFA that runs both machines simultaneously and accepts a string if either machine accepts it. Since we can always build such a DFA, the union is regular. Example, if L1 is a set of all strings made only of A's and L2 is a set of all strings made only of B's, then L1 union L2 is the set of strings that are all A's or all B's, still regular. Now intersection. The intersection L1 intersection L2 contains strings that are in both L1 and L2. The proof is similar, product construction. But this time we accept only when both machines are in an accepting state. Example, L1 is strings with an even number of A's and L2 is a string with even number of B's. The intersection gives strings with an even A's and even B's. That's also regular. Now moving on to concatenation. The concatenation of L1 and L2 is the set of all strings formed by taking a string from L1 and joining it with a string from L2. For the proof, we build an AFA by taking NFA for L1 and the NFA for L2 and adding an epsilon transition from every accepting state of M1 to the start state of M2. The resulting NFA accepts L1, L2, which can convert to a DFA, so it's regular. Next is the clean star. L star means 0 or more repetition of strings from L, and it always includes the empty string epsilon. To prove this, we add new start state and epsilon transition from every accepting state back to the original start state. This allows the machine to loop as many times as needed. Now let's look at the complement. The complement of L is the set of all strings over the alphabet that are not in L. The proof is elegant. Take the complete DFA for L and simply swap the accepting and non-accepting states. Every string that was rejected is now accepted and vice versa. On the important note, the DFA must be complete, meaning all transition must be defined for every state and symbol. If there are missing transition, we add a dead state before the swapping. From complement, we can easily derive difference. L1 minus L2 is the set of strings in L1 but not in L2. Now let's look at two more operations, homomorphism and reversal. A homomorphism is a function that function h that maps each symbol to one alphabet to a string over another alphabet. If we apply homomorphism to every string in a regular language L, the result h of L is also a regular language. The proof: replace each symbol in the regular expression or NFA for L with its image under h. The structure remains finite and regular. Finally, reversal. It is the language formed by reversing every string in L. For the proof, take the NFA for L, reverse all transition arrows and swap the start and accepting states. The new NFA accepts exactly the reversal of L. Now, why closure properties? It is used in lexical analysis in compilers. It's used in text search and grep for formal verification, firewall and packeting filters. These are the application of closure properties. To conclude, regular languages are a powerful and simple class of formal languages. What makes them even more useful is the fact that they are closed under all major operations. Like we discussed, union, intersection, concatenation, clean star, complement and difference, etc. Thank you.